In my experience of languages I've worked in and industries I've worked in, most other fields are specific to the field itself. I've never seen this level of passion specifically for a language, and the enthusiasm and level of detail and knowledge and attention to detail about nuances of very small parts of a language. And that extreme attention to detail has been really cool to see.
Hey everyone, so I wanted to talk about kind of an interesting topic. This is latency and cache coherency. And I have an example of kind of a live environment that we would see kind of in the trading space. So there's a lot going on in this diagram. It's going to be a little hard to explain, but here, the ideal problem here is that, or the solution really, is we have some sort of a network device and we want to read in some network data in packets. And we want to DMA it to the host's memory, and we want to, let's say, read it from multiple threads on the system. So a DMA basically is how do we get data from the FPGA or network adapter into the host without CPU intervention. So there's a DMA engine that you can use with a kernel API, and you'd want to do this because you'd want to bypass some of the kernel stack, which includes copying data from kernel space into user space. And what this does is if you DMA data directly from a network device into user space, you can avoid a lot of that kernel stack. And in some architectures, this might be an L3 or DRAM, and this is through the PCI bus. So if you have multiple readers reading from this data on the host, you might encounter a lot of cache coherency traffic and some problems if you kind of want to minimize on latency. So this is kind of a small experiment with a couple of code blocks just to illustrate an example. But on the left-hand side, you have some code that calls the kernel API to allocate a region of memory for a specific amount of pages so the FPGA or the hardware could put those packets into memory. And on the right-hand side, you have some user space application that, for this example, timestamps the system clock before the hop method to receive the packets from the DMA region into user space, and following that is just a simple line of code to read it. Please excuse the use of C and not C++ in this example. So here's a diagram of the latency. These two are perf counters, reads to core, and demand data RD. And this benchmark is not comprehensive. There's a lot of things wrong with this that some people can mention, but it does prove my point, which is why it's here. You can see with the one thread, there's about 12,000 events that happen on this Intel system. And using two threads, these two perf counters increase to tens of millions. And what it means is that these counters measure how many times other cores read your cache line and how many times your core reads other cores' cache line. And you can see it kind of stales around to 2, 3, 4, 5, 7 threads, but it's very minimal at the first thread. And the nanoseconds on here, it's kind of small, but for thread 1, it's 1250, and for 3, 5, 7, it's around 1350. So the nanoseconds itself they really have no significance since there's different hardwares around, but you can see the percentage that it's a pretty big difference. So why that's kind of happening is kind of based on the hardware here. And you can see that each core/tile, this is a Intel Sapphire Rapids diagram. You can see that each core has a slice of the L3 cache. Generally, we kind of talk about how the L3 cache is shared amongst all the cores, but that doesn't necessarily mean that each core has the same latency to access that cache. So you can see on the very top, it says PCI X16. This is where the hardware FPGA or network device comes in. And Intel has this new technology called DDIO that can DMA a lot of this network data into L3 cache directly, not DRAM. So when your cores kind of read this data, this critical network data you have, it'll go to L3 and not DRAM if the data coming in can fit in L3. So a couple things I wanted to point out is that one thread is not equivalent or not arbitrary to multiple cores. you can have one thread reading this memory region from the FPGA into host memory be a lot more quicker because it's closer to the tile that's connected to the PCI device. And another point is that let's say you have a multi-socket system with 2 NUMAs. You'd have to travel over the UPI, which is at least 50 nanos, to access other remote data. So if you have a thread on a remote NUMA and you have your FPGA or network device on another NUMA, you're going to sacrifice a lot more latency and snoop timers. There's also a hardware prefetcher in the BIOS that some systems come with that can prefetch and cause more coherency traffic. That's pretty much it.